So for our Module 10.2, we're looking at the topics of rivets, welding, and bonding. Some objectives and topics we're going to cover here include rivets, taking a look at different types of rivets, different applications, and some of the governing equations. Talk about the welding process, looking at our static, axial, and direct shear loading, static torsional and bending loading, as well as our fatigue considerations. Then we'll get into some of the topics, looking at brazing and soldering, and then get into some adhesives as well. So within this module, we're going to go over some of the theory for these topics above, talk about some of the governing equations we're going to apply, look at some practical applications, and then go through some problems together. So this relates to our chapter 11 in our textbook, again with the topic of rivets, welding, and bonding. So first, we're going to take a look at the topics of rivets. We're going to talk about a couple different types of rivets that we've seen commonly. One thing to note about rivets is these are a very widely used and common connector. So applications we can see these in, we can see them in the aircraft industry, transportation, different types of buildings, bridges, ships, boilers, tanks, and I'll get into a little bit of how I use them with leather work as well. So there is a large variety of applications that rivets can be used, and within that there's a lot of different types of rivets, and each rivet is going to have its own place. So there are some things to consider as you're speccing out which type of rivet you're going to use for your application. This will tie back to our design process, and we'll really think about what types of loads are these going to see, and what directions are these loads acting in. Now, a thing also to think about with these is there are some highly controlled standards in which we're going to follow. So two of these are the American Institute of Steel Construction, AISC, and the American Society of Mechanical Engineers, ASME, as well. So both of these have some standards that we can refer back to when we're making that decision on what type of rivet we need for our application. So as we begin our discussion with rivets, first let's talk about them in a very general sense here and not look at any particular type. So a rivet in general is going to be made from a ductile metal. So this could be a carbon steel, aluminum, or brass. And again, different applications are going to require a different type of material. One thing to think about with this here is not only your strengths that you need these or which direction your loads are going to act in, but also your environment that they're going to be used in, how often they're going to be used. So if it's a corrosive environment, then maybe we don't want to go with a carbon steel. Maybe we need to go with an aluminum or a brass as the first two types that we can consider. Or maybe we need to do a stainless steel as well. So there's different types of materials that these can be made from, but typically it's going to be a more ductile material due to the nature of how we're going to actually apply these rivets. So within the types of rivets that we can look at, there's tubular rivets and blind rivets. So the main differentiation for when you're going to use these is with how you can actually apply them, where you can get at them. What is your access to the material you're using? So if we're talking about a tubular rivet, you're going to need access to both sides of the joint right there. You need the top and the bottom of this. And a lot of times this is not possible. I know when I'm doing motorcycle seats and putting leather on those, I can't use a tubular rivet, even though I may want to use one of those, because I can't get in. I can only get at one side of it, and then it goes up inside of the seat under the cushioning. So I end up using a blind rivet for that right there, where I only have access to one side of the joint. So that's just one particular case where I couldn't use a tubular rivet. I had to use a blind rivet from that, just based upon access. And then as I think about there, well, it's going to be outdoors. It's going to be in a all-weather environment. So therefore, I probably don't want to go with something that could corrosion would be an issue with. So I can think about different types of metals I can use for those rivets and see what is available for the blind rivets. And then from there, we move on to what type of machine, what type of tools do we use to actually apply these rivets. So rivets have been around for quite a while. We're going to take a look here at an application from back in the past where rivets were being used in the structures of buildings. So what would happen here in this situation is the rivets were going to be heated up in a furnace to a glowing hot temperature. So you can see the furnace over here. Now you have this furnace operator guy right here, and he would use tongs to individually remove. So you can see the tongs right there in his hand in order to individually remove and throw them to the catchers who are both stationed by the joint that need to be riveted. So you see you got your two catchers over here. Now what the catchers would do, the catcher would place the glowing hot rivet into the hole to be riveted and then quickly turn around and wait to catch the next rivet. So one worker would, of the two catchers over here, would hold the heavy rivet set. So you need a set right there for the rivet to go against the back round head of the rivet. Then the hammerer would then apply the pneumatic rivet hammer to the uniform head, causing it to mushroom shape just tight enough against the joint until it reaches its final dome shape. So they're manually hammering these into spot. Sometimes they did have to do it with a hand hammer. Other times they did have these pneumatic rivet hammers as well they could use. You can see down here, there's the pneumatic line going up to the rivet hammer right there. And you see you got one guy holding it with the set over here and one guy hammering it right there. And you get that shape to compress it together to hold that joint together. So that leads us into discussion to talk about manual rivets right here. So here's a step process that we can go through. Here's what a manual rivet looks like right here. Again, this is why it was a more ductile, softer material right there. Here's the two pieces of material in step one right here. You can see there's a little gap between the materials as they slide through the hole in the materials. A pre-punched hole in the materials for this case here. Then what you do is you take a shape like this right here. This hammers it down and brings these two materials flush together. Then there's excess amount of rivet. You can cut that off in step 3 over here, and then you begin manually hammering and shaping this with a ball peen hammer right here is what they're using until you get a slightly rounded shape. Then you get this set right here that has that domed shape into it. And you see there's a set on the top and the bottom. The whole way through you have your bottom set in over that round head of the rivet that fits it perfectly. Then you add one to the top right here, finish hammering it in, and you get that perfectly domed shape right there. And now you can see this is holding, this rivet right here, this manual rivet is holding these two pieces of material together. So now with those manual rivets, that's quite a bit of work. You definitely need the set. You need the skills, you need the knowledge in order to know how to use these and experience to get it just right, get the right amount of force on that. Again, you're manually hammering this in, making the shape of that so it fits in the set just right, and then compressing it to get that perfect dome shape at the end. You want to make sure it's compressed just enough to hold those two materials together. Now there's also automatic riveters as well. So we can see an example of one here. This one is an air pressure and electric. So there's controls on these. Some of these are very fancy. You have all types of feedback controls to get just the right amount of pressure. You can see there's the rivet handler right here. Some of these even have an automatic feed that lines up the next rivet in. And this again is kind of a generic automatic riveter, but we'll get into a little bit more depending on which type of rivet we're using and look at the different types of rivets that are available out there and see how these can vary for what types of automatic rivet and manual rivet machines can be used. So in modern construction, high-strength bolts have almost completely replaced the structural rivets that we saw in that previous slide there. And reasons why we've replaced these rivets with these high-strength bolts is, one, it's expensive. You saw you had a team of 3 to 4, maybe even more highly skilled riveters are needed to install the rivets in one joint at a time. Two relatively unskilled workers, on the other hand, when we're talking about these high-strength bolts, can install and tighten high-end bolts. And oftentimes you can even do it with one guy as well. So greater strength and connection with the bolts, cheaper, and they're earthquake resistant right there. So the issue is with rivets is it's not very easy to go back there and tighten them up. If things loosen a little bit during an earthquake and they shake a little bit, you can't go back in and tighten them up. With the bolts, these high strength bolts, you can go back in there, you can tighten them up, you can have a double locking nut on them. We could have different types of adhesive and Loctite on those, anti-vibration nuts on those, all types of things with the bolts that have kind of gone and replaced the old ways of using those structural rivets for the building construction. But there are still many other applications where rivets are commonly used nowadays. Some of these include automotive, your appliances, electronics, furniture. You'll see it with apparel, handbags, sometimes simple plastic assemblies where the element may need a covering, joints where rotations are needed, and this is allowed with the rivets, or materials that can't be threaded. So a lot of times you'll see this in fabrics, composites, polymers, and I use it personally a lot with leathers as well. So within rivets, one of the types of rivets that we're going to take a look at that we talked about earlier was tubular rivets. So again, you need access to both sides for these tubular rivets. But what we can see here, within this, we can break it down into semi-tubular, tubular, and compression. Even within tubular, what you have is you have a full tubular, a split, and a self-piercing. So these are all different types of rivets within the tubular family that can be used for various types of applications. So what we can see over here, we got the semi-tubular. You can see this little bit down here is hollow. The rest of this is going to be solid. It's very sturdy. So when you go through the two materials right there, it's almost solid. By the time you round it over in the end right there, you have a solid interface in the center of that, and it's very structural. So that's a semi-tubular rivet. They have their place. They're a little bit heavier. That could be a downside for certain applications. Sometimes you might not need as much structural support there. Also takes special types of tools, especially with the automatic ones, a very industrial strength, heavy duty press is sometimes needed to apply these. Then you have your softer materials over here when we can use a fully tubular rivet right there. So we can see this is hollow almost all the way up into the head. And some of them actually do go hollow all the way up into the head for the ones that I utilize there. So even after you complete it there, you can still see there's a little bit of a hollow section right there that goes through. For light metals, then you have what we have here is a split rivet right there. So you can see the shape of this comes through, and these kind of come over and lock back right in spot and dig into the material as well. And then you have your self-piercing ones right here. So maybe your hole didn't go all the way through or didn't have a hole at all. So these ones you can see just a small shape like that, but they're also pointed right down there at the end. So these can pierce right through into the metal like this, and this is what you end up with here. And this is great for some of the heavy metals down here. Then what we have, the last one here, is a compression rivet right here. And the benefit of these is they're less likely to split the material. You can see one kind of slides into the other like this here and holds in spot. Now again, all these will have their pros and their cons and their benefits of when we want to use them, what applications, what loads we're looking at, and what we're looking to do with these rivets. So I want to relate this back to some of the work that I do, and these are the type of tubular rivets that I use right here. So these are a steel construction rivet right here, which is nice because with the manual press that I'm using right here, because it is ferrous, I can use a magnet built into the top head of this to hold it in spot. And a lot of times that is very useful. I'm holding my pieces of leather, my materials down at the bottom that I need to align things. I need to put a buckle on it, I need a strap on it, I'm riveting two pieces of leather together, and I need both hands for that to line it up. I can't hold the rivet there as well, so it's nice I can see I also use a washer because this doesn't quite round over enough for what I need to do to hold it in spot, especially with a really soft material like a leather, so I need a bigger surface area right there so that the whole rivet doesn't pull right back through, stretch the leather and pull back through. So I'm using a tubular rivet with a cup washer that will dig into the material as well to help hold it in spot. So this is what I use right there. You can see right here on the top of this, this is where the magnetic holds the head, the rounded head of my rivet right there in the spot there. And I have a little cup system down here that I put my cup shaped washer in, and then that's ready to go. I can put my two pieces of material or my buckle and my piece of leather in there, and I can pull down with a mechanical advantage here with my press right here. And this is a 1-ton press right here, and I get some good force. I can hold that right in spot. And it locks in, rolls over the rivet, over the hole in the washer right here, and holds it in spot perfectly. So this is what it looks like. Here's my application. Here's a leather belt right there. I needed to rivet this buckle in spot. You can see there's the round head of my rivet right on the top up here. And I use that. That's what's, again, is being held up by the magnet on the top of my manual hand press right there. And then on the bottom side, inside of my belt right there, I put my washer in that cup on the bottom side of my manual press. And you can see now it rounds right there, the edge of the rivet over the washer right there, and holds it in spot. Now I've done manual testing with these on tension testing machines to check to make sure that this is not going to pull through. Now I'm not pulling this in pure tension, so the force is going to be coming across, going in this direction here with my buckle as it pulls with the ladder strap. So that right there is going to be causing the force to go and shearing this right here rather than putting it in pure tension. But what that can do is that can elongate the hole and deform the hole in my leather. And if the hole in my leather deforms a little bit as that stretches and stretches, I need to make sure that this washer is going to be big enough so even if the hole deforms, it's not going to pull through the leather. So again, different applications, we need to think of different types of rivets that we could use. Now, standard applications like this, a lot of people don't use rivets in this situation. Just like we talked about with the construction building, sometimes it doesn't make sense to use a rivet. A lot of people will go, for this case here, with a spider nut that they'll put on the bottom side there and a screw, a low profile truss head screw right here that threads down into that and threads in to the spider nut that digs in with the prongs into the actual leather there. And I did a lot of testing, back and forth analysis, debating between the two of these, and the reasons I ended up going with the rivet were two main reasons. One reason being I didn't want people to be able to remove the actual buckle, because over time, if that screw can loosen, eventually it could loosen too much, and if they don't tighten it down well enough, the Loctite wears, then eventually that could loosen up, and in their lift, the buckle could come off. And I didn't want that to ever happen. So I decided to rivet that in spot right there. Now the other reason I didn't like using the spider nuts is because it does have those prongs. If I don't want it to rotate, that digs in leather, and eventually it can turn and rip and rip and rip and actually destroy the leather and rip a big gouge in it, which makes it less sturdy as well, less strength, and an easier chance for the whole thing, the spider nut and everything, to pull through if those sharp prongs are ripping and tearing a hole and cutting into the leather. So for that reason, I decided that rivets were going to be the best option for me, and I chose to go with these industrial strength tubular rivets with the washers, all made from steel, for my application. And there are other type of rivets that we'll get into, some rapid rivets and double rivets that I looked at and just did not work for this application, didn't have the strength that I would need. And a lot of this, we do have some calculations that we'll get to later in this lecture on how we can calculate rivet strengths for your application. But also, as we've seen in this class, there are some unforeseen things that are hard to fit into our analytical solutions that we actually just need to go out there and do some testing. So that's what I did, is I put these on an MTS machine with something that expanded radially to put pressure on them as it would in a real life situation. And with that, I was able to take a look and see when certain rivets would pop, when other ones weren't, and where the failure would lie within this here. So what I found is going up to 1,000 pounds on a testing machine, the leather would stretch before anything would pop out or get destroyed. So these rivets held up for over an inch of deformation as we're expanding outwards with the leather. So these ended up being the best rivets, whereas if I went some the double rivets or the rapid rivets, they would actually pop under these tensions. So here's another application where I use these. These might be a little bit overkill in this situation, but these are dog collars that I utilize these for. And this is just, you can see right here, I do have, turn on my laser right here, right there and right there. You can see the top head, the round head of that tubular rivet right there. And I have different lengths of these for different applications depending on how thick my material is. And that's another calculation that you're going to need to take a look at to figure out how much rollover you're going to need over that there to hold it in spot. You don't roll it over enough and all of a sudden you can pop a rivet, even one of these industrial strength ones. So you got to make sure you have the right pressure to get the right amount of rollover, which is a calculation within itself. So you can see on the inside right there, there is the washers with the rollover from the tubular rivet. And what you can see here is on these, I have a solid stainless steel D-ring here, which the leash attaches to. So when the leash attaches that, you're pulling on that. So this here almost does pull these guys right into tension right here when you're pulling up on this D-ring, coming out with that force there. So if you're coming up with a force off of your D-ring right there, you're pulling against these two pieces of leather right there, trying to pull these apart with that D-ring right there, moving it up. So you do put these in tension rather than just in shear right there. So with the weight belt, we're pulling across the side. With these dog collars, we're kind of pulling out and putting it right in tension at axial load. So this, I really do want to make sure I have enough rollover like that. You get a good impact load if a dog takes off, sees a squirrel or something, and you're on the leash. You want to make sure that that's not going to rip out, so you want enough strength with that there. And I ended up doing a double rivet with this as well, just one on each side of that D-ring there to distribute the load. Now with those tubular rivets, especially using the washers, they're not the easiest thing to install, especially if you don't have the appropriate and expensive tools and presses to utilize these that are special made. And every type of rivet takes a special die that fits into that press that you have to have custom made for a lot of these. And it can get expensive. It's not very portable. So there's other types of rivets that might be cheaper, easier to use, and more available, more readily available to use. So some of these are the double rivets or the rapid rivets, and I use these in certain applications within my work as well. So we can see what we have. We have a technical drawing over here, all of our key dimensions within these. You got your head of your rivet up here, and you also have your stem down here. So those are the two main parts. You got your head and your stem of the rivet, and what you can see on the stem side of this part goes up and into the head of the rivet, and when you press them together, what you end up with is this here with your two materials sandwiched in between, wherever that hole was there, holding them together. So these rapid rivets are quick and easy to use. There's cheap manual sets you can use, but there's also presses, pneumatic presses, hand presses, and there's even a hydraulic press as well you can utilize with some of these, and even some of those like we saw at the beginning of this lecture here, some of those automatic gun presses that you can utilize with these. So these are a great, quick, cheap option, different types of materials, different types of colors, but if you think about what's happening here as you're pressing that in there, it's just deforming this little head just a little bit, kind of pressing it up into this area here, and that's not very structural. It's stronger than you would imagine, but when you're talking about, 1,000 pounds of axial load on this, they don't always hold up and they can pop. And even in situations where I've used these for fashion belts and other collars and bracelets and things like that, you get a good yank on it, sometimes you can pop those up, especially in impact loads. So I don't like to use these with dog collars at all. You get the dog to yank on your leash, these things could pop right open and your dog can run free. So I don't like to utilize these for that application, but for other types of fashion applications, I can use these all the times. Handbags, purses, things like that. These work great. They're very fashionable, a lot of different colors, a lot of different shapes, sizes. They've even got ones that are designs and everything on them as far as aesthetics go. But what really comes down to is you got to make sure that they're going to hold. So we talk about different presses, different types of tools to utilize these. This is my multi-function press that I have here. Here's the manufacturer's picture of this, and this is great because it's a foot press. So before I talked about needing to use both your hands to hold things, well, sometimes you actually have to use both your hands to hold it, and you can't let go to pull a manual lever. So this is right here. This one's got a foot lever, so we got a mechanical advantage that comes in through here, up top here for another mechanical advantage, and this pushes this down here when you step down on this foot pedal right there. So there in itself is a great engineering project right there. Going back to your statics class right there, looking at those loads right there and seeing what we could get for a force in here and make sure it's enough to do the right type of rivets that we're going to use. I use this for snaps as well. But again, with this here, it's a multi-one, so I have different adapters that I need for different types of rivets, different sizes of rivets. I can manually adjust down here with this thing for the different lengths of rivets, but as far as the head sizes go, it does require different attachments for this. So it's still not the cheapest and easiest, but if you're doing a large-scale production, this is something that we do need to think about. So as engineers, especially in a design class like this, we need to stop and think about how many we're going to make. And does it make sense? We talk about cost analysis, and cost is also your time as well as what the individual material cost is. And as you buy more of something, material cost goes down, typically when you buy in bulk, and the amount of time it's going to take. So maybe you can get a hand set for one of these. You can set it all up and align it, and it's going to take you like a minute or two to put in a rivet. That's fine if you're making a couple of these as prototypes, no big deal. But all of a sudden, this cuts it down to 5-10 seconds each. Put the two pieces in, put your piece in, step down the foot pedal, go to the next. If you're talking about a large-scale production, something like this is very, very useful. And we can even take it one step further, 2 or 3 steps further actually, when we're talking about riveting things and automating it and making it a little bit easier to save us some time. So with that, you can take a look here. Here is my double rivet. You can see I have this top piece. It's a pretty simple design up top here. Not all of these are going to be a ferrous material, so I can't necessarily use a magnet. What this is a little piece of rubber up here that just folds over the top head of that rivet right there, holds that in spot, and on the bottom, this is spring-loaded right here, so it makes it blind. You can see when it's all the way up, you can't even see the stem part of that bottom rivet right there. Holds that in spot. What I can do is I can put my materials, push it down, and then the stem comes right up through the two pieces of material. Those are my two pieces like of leather right there, and I have a thicker piece up top there with the hole down the center. Line it up, I step on the foot pedal, it moves this down, presses the two pieces of material together, pushes that top head over the top of this, and now my two materials are down in between the head and the stem of this right here, locked into spot. So again, you can see all the different types of attachments and things that we can use there. And again, this is a great foot pedal. I can utilize both hands, but I still need to manually put the head and the stem of the rivet into spot for these double or these rapid rivets. So the next step we can do with automating these is we can put in an automatic rivet feeder. So you get a big hopper up top here, and it has a sorter inside this that automatically aligns these rivets. You can see these are all going to fit in just perfectly, feed down from the top here, and then you have your set down here at the bottom, whether you're using rapid rivets or you're using tubular rivets or you're using tubular rivets with a washer. There's different types of adapters you can get for this right here, and this is that same multi-function machine that I showed on the previous slide there. And if you're doing large-scale production, sometimes it makes sense to do an investment and get something like this where you can speed up your process, where now I don't even have to feed the rivets in or set them in manually anymore. And a lot of times that is a lot of time. You're just putting your material down, reaching over here, grabbing the rivets, putting them in and going. Now I can literally just have all my leather pieces or whatever it is that I'm riveting lined up, step on the foot pedal. But the thing to think about this is still, though, a manual machine in the fact that I am giving a mechanical advantage by stepping on it, putting my body weight onto that foot pedal in order to compress the rivets. Now, as we get to some heavier duty rivets, this might not give you the force you need to do that, especially if you're doing with a stainless steel rivet or something like that, where it's not quite as ductile of a material, and it's going to need a lot more force to round it over in order to achieve that shape that you need after the materials. Even if it's just over a washer or if it's not, you're still going to need quite a bit of force for some different types of the rivets, especially as you move into the tubular and semi-tubular rivets. So that's where we think about, well, one, just repetitive motion, maybe just standing on it, putting the force on it, even if the machine can do it, can get tiresome after a while. maybe we want to move to a pneumatic. So that's what we have over here. In this next picture here is pneumatic riveter here. And you can see this is very similar to the hand manual rivet that I showed earlier that I was doing with my tubular rivets with washers. But now rather than having the handle coming out the front that we're pushing down on, we come off the back, come down here to a pneumatic piston with, and this is the beauty of this too, pressure setting. Because with these types of rivet machines, you're manually addressing the height to get just the right amount of compression on there right there. And there's not really a feedback sensor built into those. So you're just figuring out what that height is, setting it just right, then stepping on it to the right distance every time in order to achieve the right amount of pressure, not compress too much and split the material, or not to go so you don't go far enough and you don't round the rivet over enough. So it's a very skilled set that you need in order to achieve the right pressure, the right forces, to get things just right, not to damage the material, and to get the rivets to the right spot that might want to roll over. So what we can do here, and the beauty of this is when you have this pressure regulator, once you've set it, you can kind of set it and forget it. You say, okay, I know I'm going to need 75 PSI every single time. I hook up my air compressor to this right here, set the regulator to 75 for whatever material I'm working with. Go ahead and just a light touch of this. It's just setting off either a electronic signal. You can have a relay in there that you just touch down when you're doing that foot pedal, or this one right here. What this does is there's a steel rod that comes up here to a relay that's built in off to the side that sends a signal down to our piston here in order for it to activate. Push up on this, push down on this, pushing this back down and giving us that force in between there. So this is great for a couple different reasons. One, doesn't take much force down here on your foot pedal. Two, you've pneumatically set this to the right pressure every time, and you can have a list. Okay, I'm dealing with leather today, I want it at this. Now I'm riveting plastic, I want it at this. Now I'm riveting to metal, I want it at this pressure setting. And that pressure setting, we can do our calculations. We've seen in our other courses, okay, if I have this much pressure going into a piston like this with this stroke right here at this diameter, then I know this mechanical advantage, and that's a great design problem within itself. If anybody was still looking for a design problem to work on, one of these is a great problem to work through. And we can take this to another level though. You still, at this one here, need to manually put your rivets and your washers or whatever it is you're using in there. You could add one of these same type of automatic feeders to this style of machine as well to automatically feed your rivets. And we're talking about large scale productions. This is something that becomes important quickly. You're talking about 1,000 pieces a day. All of a sudden, a machine like this is well worth the investment. So we talked about tubular rivets and how you need access to both sides of your material right there. What about the situation where you only have access to one side? And I mentioned in this one here, for my application, if I'm putting leather over a motorcycle seat and covering it, and I'm coming around, wrapping around the bottom of the seat, I no longer have access to the top. I only have access to the underneath side, and that's all that's seen. So that's where I end up using blind rivets for that case right here. And there's, again, different types of manual ways to apply these and different automatic, different guns and things that we can use. So we'll take a look at 3 different types right here. We'll look at the self-plunging blind rivet, the pull-through blind rivet, and the closed-end mandrel brake blind rivet as well. So what we can see with these is when we have these blind rivets, this diameter comes straight down through the whole of our material, so we can easily push this through from this one top side that we have access to. We don't have access necessarily to this bottom side there, so we're coming in from the top side there. It's coming down through, and then we have this pulling head here. So this pulling head, what this is going to do is going to pull this all the way up here as we push down on that there, and this is driving this up here, which expands this right here. So now this is larger than the opening, locking that in spot there, and then the mandrel breaks after seating, and the rivets expanded down here. Then you're still left with this little bit of nub right there at the top right there. It never breaks quite evenly right there. You still need to do an extra process of trimming or grinding down the mandrel right there, so you have that nice smooth shape at the top right here. So this is the self-plunging blind rivet. Now we also have the next one here is a pull-through blind rivet. So this one here, same type of application. You're still pulling up through this right here. This is all same diameters. It slides down through the hole in our materials right there. Then you can see the shape of this right here. As you pull this up through, it's going to pull that in a spot around it, deform our rivet right there. So that's still going to expand so that it can't pull through the actual material anymore. But now what happens is this mandrel head collapses as the rivet expands. And what this does is it pulls right through, leaving you with a nice clean top right there. So you don't have to worry about this trimming or grinding of the mandrel. The last type that we're going to take a look at here is our closed end brake mandrel blind rivet right here. So we can see the difference is the first two are self-plunging, and our pull-through all had this little piece of the mandrel that stuck out there that was going to push up into the rivet. This is all internal right there, so that's what they call it, a closed end of the rivet right there. So then we pull up on this, push down on this right here, it pulls it through, and that mandrel, once this pulls this up like this, it ends up pulling the bottom of this, the blind side right there, and this again deforms this big enough so this can't pull back through, but then the rest of the mandrel breaks off and you have a nice clean surface right there. So these are 3 different types of blind rivets that you could utilize for whatever situation you're dealing with. Different types of tools will be used with each of these different types of blind rivets. Now there are a few other types of blind rivets. We'll take a look at 2 more of these right here. These are kind of combinations of the other ones, just slight variations as well. You have the open end brake mandrel blind rivet, where you can see the same type of situation right here, where again you're pulling up with this right here. It's deforming the shape of this out here so it expands, so rivet can't pull through, but you still do have a little bit right here of the actual center mandrel right there that's sticking out. And what you can see now, the top does break off, and you do have this nice clean rounded top there. Then you have the pin drive blind rivet, and this is interesting right here. So this one is a little bit different than what we've seen before. So rather than all these other ones we're pulling up in the mandrel like this right here, this one we're hitting the pin and driving it in this way. So this is simple. This is something you could do with just a hammer. There are automatic ones of these as well. And this is great for situations where you don't need a through hole right here. So for wood, plastic, and metals, you can just hammer this whole thing right through as if it were a nail, and then it expands like this once it goes through the 2 pieces of material right there and locks into spot. So again, different applications for each of these different types of rivets. And that's something you really do want to consider when you're looking to decide what type of rivet you want to use. What type of materials are you working with? What type of tools would you need in order to install these? What materials are each of these types of rivets made out of? All those things are considerations when you're choosing which rivet's going to be best for your situation. So now I talked a little bit about the necessity of getting the right amount of pressure, installing these, getting the right amount of rollover for the rivets, and this is something that, again, as I mentioned earlier, is something that's a bit of a skill that's learned. This is definitely a skilled trade, installing these. Now, with these automatic machines, if you're in an assembly line in a factory, yes, you still need the skill to know what pressures to set things out, and you also need to be able to look at it and determine, is this good or is this bad? So this right here is kind of a little cheating chart right here, so you can understand, okay, what is a good install right here, is the right amount of force, right amount of pressure. What should it look like? What shouldn't it look like when it's installed correctly? So we can see right here, take a look at this application in the center right here between good and poor. This one's pretty easy to see for this style of blind rivet right there. You can see where it's good. You've pulled this up enough so there is no gap. That is a tight fit right there, and there is no wiggle room. So this is a visual inspection, but again, these are blind rivets, so you might not be able to see everything within a blind rivet. So also a test right there. So even if it's just a manual feel test, maybe you don't want these to twist. Under a certain torque, maybe they shouldn't twist at all. So that's something you can see there. Whereas if a poor installation right here, you can see there's a big gap there. This doesn't even put any pressure in between those. You can still probably pull those 2 pieces apart, and you'd end up with a gap in between these here. They could easily twist, come apart. You have not done the installation correctly on here. This would be a poor installation example right there. Now, another thing to think about, even with the blind rivets, is sometimes it's difficult even to get at one of the areas. So different types of tools, different types of apparatus. Sometimes they have things that have 90 bends on them. So something like this is really difficult to get at. So a situation like this here, you can't necessarily come down from the top all the way. You know, if it's cut back like this, sure, then you can. So maybe you need to come from the other side and get that good seal right there. So which side you come from can be important. And sometimes you don't really have a choice for the situation you're in, where the rivet needs to be located. You can only come at it from one side. So maybe there's a better rivet choice for those type of applications. Now, if we are dealing with a softer material, like I am with a lot of the leather work that I do, a lot of times you can see putting a washer in line, even if you're using some of these type of rivets right there, is a good idea, because then it expands that surface area right there. So as you're pulling through in my application, where you're going to might have a lot of tension on it right there, you don't want, when this hole expands in your soft material and it deforms that shape, you don't want this portion of the rivet to pull through. So if you have that washer there, it increases that surface area right there and doesn't allow it to pull through. So just other applications to think about when you're dealing with these, and again, specking out which type of rivet is going to be best for you. Think about all these different things, then take a look at all your different options for the rivets and decide which would be the best fit for you. So now as we're talking about our strength when we're dealing with rivets, we're looking at our tensile and our transverse shield failure. We talked about this a little, again, depending on how you're pulling on the rivets. A lot of times it can be in shear, sometimes there can be some tension or a lot of tension for an axial load on it right there. This is the same type of things we ask ourselves and look at when we're dealing with our threaded fasteners as well. But just now they're without threads, so no thread compression or stripping there that we have to worry about or deal with. So a thing to think about is during the installation, if we're doing a hot installation, this is going to be achieved by contraction during the cooling if it's installed hot. So with those type of hot rivets right there, the friction is going to hold the part together and it will tend to lose tension due to creep and stress and relaxation. So something to consider if you are doing some of the hot installations like there were on the building example that we showed. So we do have some general governing equations that we can utilize when we're dealing with our rivet initial stress. So these are similar to the axial stresses we've seen before, but now we have these axial stresses for our rivets right here. So we can see here we have our sigma for our axial stress right here, our normal stress. This is equal to our P over A, our load over our area right there. Well, if we're dealing with a round rivet, we can replace this for our area, and we can put this over here, and then we can see we'll have a 4 on the bottom of this here that we can move up to the top to the numerator. So this is going to be 4P over pi d squared, but we also do want to consider we need to add in our residual stresses as well. So if we're dealing with our axial stresses for our rivets, this is our equation right here. Our sigma is equal to 4p over pi d squared plus our residual stresses. Now, if we try to take a look at our shearing stress, whether it's a single shear or a double shear, we have the relationships we see down here. So we have our general equation for our shear stress, that tau is equal to our load over area. Again, we can replace our area, and what we end up with here is 4p, 4 times the load right there, all over pi d squared when I plug in for that circular area. You can also see, though, if we're dealing with a double shear over here, it's similar to what we've seen before in other applications. We're dealing with double shear stress. Our tau is going to be equal to P over A. Again, we can replace that now, but it's a double shear, so the difference is now this is going to be 2P over our pi d squared as compared to the 4P over our pi d squared there for double shear as compared to our single shear when dealing with our rivets. So due to the fact, as we discussed at the beginning of this module here, that our rivets are made of a ductile material, a lot of times as the rivets deform and fail, this can cause a failure in the material from that. So we can see we have a couple different examples down here. You could have an example A, we have shearing of the rivet right there. So as we're pulling on this material here and this material like this right here, you can see here the rivet could shear in between those. You could have tension in the plate between the rivets right there. So in between these guys right here, you can see the tension in our plate. We could have failure in compression. So what we can see is as we're pulling this right here and the rivet, this is pressing into this right here, and we can see now the actual material right here is deforming right there. This is enlarging that hole there. We could have shearing at the edge of the plate. We could have tearing as well. So you see your shearing right here, and then you see your tearing right there as we're pulling this, and those are the rivets. Now, one of the benefits to rivets is the fact that they're not going to loosen during fluctuating loads, unlike threaded fasteners. So again, as I discussed for my project with my weight belts, this is one of the main reasons I chose to go with rivets instead of a threaded fastener, or in my case here, a spider nut and a truss-headed screw, because I didn't want it to be able to loosen during fluctuating loads. And that's exactly what we have, expanding, contraction, as people press out against their belt for support. I'm going to be seeing that constantly on those, and I didn't want those thread and fasteners to loosen. So that's why I chose to go with the rivet right there. Now, the downside can be that these are difficult or unable to disassemble. So that's a big issue right here. If somebody wants to replace a buckle or a ladder strap or something of those breaks and they want to replace it, they need to send it back to me. I need to physically drill out that rivet, and then I need the actual rivet machine, which is big, expensive, and not easily portable, that not everybody's going to have at home. So then I need to put on the new buckle for them and reattach it, so that if one of my buckles fails or they need to move it back to change sizes, then they need to mail it back to me. I need to cover the cost for shipping to send it back and then change it. But to me, I would rather deal with that than to chance the fastener coming unthreaded, loosening, and having the belt fail on them during use. So this is where this can protect the components or the actual people using it. So that's, for me, a big benefit to the rivets, and that outweighs the fact that it's not very easily disassembled. And with that, it's not sustainably minded as well in the fact that the old one's getting drilled out and thrown away. So I'm wasting a rivet if I do need to replace it, rather than just unthreading a screw, putting a new part on and threading it back in and being able to utilize it again. Once I've disassembled the rivet, you need to throw it out. I literally drilled it out and destroyed it. So next we'll move on to the topic of welding. Now the benefit of welding is this allows for simple shapes to be combined to make more complicated structures, and this eliminates the need for us to use casting, machining, or riveting that we just talked about, or even bolting. So within welding, we're going to take a look at some simple connections right here. So we have a couple different types of welds. We have a butt weld, a T-weld, corner weld, lap weld, and an edge weld. Well, what is a butt weld? Well, then butt welds we have right up here. You can see these two materials are butted together right there, the two flat surfaces, or we can have a single V as they're butted together, even a double V, a single U, or a double U. So these are all examples of butt welds that we could use for these different types of weld joints. Now, when we're talking about our T-welds right here, we have a couple different options as well as far as we set these up our materials. We have this option right here for a typical T-weld, where again, you just have those square surfaces right there butted together like that. You have a single bevel right there. So you see there's your single bevel right there, which makes a nice little spot for you there. You have a double bevel, so now you can come at this from both sides there. A single J or even a double J. Then we get on to our corner weld. So for corner welds, you can have it just so these two corners just barely meet right there, giving you this whole area there. You can have it slightly come over here for a corner weld like that, or you can even have with these two beveled edges like that right there, which again allows you a nice little trough there. Then we get into our lap weld. Here's our example of what a lap weld would look like as it overlaps right there. Then you have your edge weld, where you have this situation going on here. Now we saw on all these different types of weld joints up here, we had these different options right here for our edges. You have your V edges. You can see that's a V right there. And again, you could even have a double V on both sides. You had a U, so you can see your U shape right here. You can also see down here is kind of half a U, which gives us our J shape right there. And you do have your double J as well. And then you do have a bevel as well that we can utilize. You can see right here, there's a single bevel, there's a double bevel right there. So what is welding? Well, we can take a look here. This is going to be a localized heat treatment that's used in order to bond metals together. Within this, we can take a look at our heat affected zone and our fusion zone. The heat affected zone is where grain structure is going to be altered. So we can see here's our heat affected zone right there and right there coming along these sides here. That's our heat affected zone right there. Then we have our fusion zone, which we can see defined right here. And our fusion zone is where the liquid metal was formed and solidified. So let's take a look at a little bit more detail at our heat affected zone. Within this heat affected zone, we can see that the material is going to be effectively annealed, and then we can see these smaller equiaxed grains. So here's these smaller grains right here in that heat affected zone. So moving from there and taking a look at our fusion zone now, so this section right here where our fusion zone is, what we can see from this, we have these long grains that grow from unmelted grains in the columns right there. So you can see these longer grains right there, and epitaxial growth right there. So there's long grains that we have right here in this fusion zone. So in this example that we're looking at, we can see is we have this single V butt weld that we're doing right here within these two plates. So what are some of the factors that are going to affect the weld and the size of the heat affected zone? So again, this is our heat affected zone. Recall down here, that's our heat affected zone right there. So some of these things that are going to affect that size right there are going to be the temperature, what we're keeping that at for our temperature range, what our time is, how long we're keeping it heated for, and the size of space to be filled or the bead to be laid down. So the size of that space is the size of the bead right here. So that space needs to be filled or the size of the bead that we're going to lay down. All of these are going to affect the size of the heat affected zone. So how far out does this go? And we're talking about the size right here. You can see the arrows right there. That's the size of the heat affected zone that we're discussing. So let's take a look at one particular type of welding. Right now, let's take a look at our fusion welding. So for fusion welding, a portion of the metal is actually going to be melted. You're going to have a weld pool, and you're going to have additional metal added to it. So you can see there is our heat source right there, creating this weld pool. Then we have, if we look back at this, our fusion zone right here. Looking at a 2D view, there's our weld pool, relating to our weld pool right here. We're melting that metal right there, and we can see there's the heat source in the 2D view, and then in the blue right here, this is now our affected heat zone right there. So when we're talking about the size of our affected heat zone, again, that's going to be back to a couple of those factors we just talked about before, one of which being the temperature of our heat source right there, along with the shape and size of the weld bead and the area that we're filling. So let's take a look at another type of welding. Let's take a look at gas welding. In particular, we'll take a look for what we're shown down here in our diagram, which is torch welding. So you can see the worker over here holding the welding torch. Now coming into this torch, you can see we have acetylene and we have an oxygen cylinder. And with these, we have a regulator on each of these, regulating the amount that comes in. So we can see our oxygen supply coming in. We're looking at the cutaway view here of our torch and our acetylene supplier here. So these both come in to our mixing chamber right here. And again, this is going to be dictated how much of each of these by these gas regulators coming in, coming down through our welding tip, where we're actually going to be using a filler rod right there going into our weld seam. So this is an example here for gas welding, in particular our torch welding. So the next type of welding I want to take a look at is arc welding. So for arc welding, what we have going on is we have an electrical arc between the electrode and components being joined, and what this does is this is going to melt the material. Here's an example of one type of arc welding that we have up here, and we'll discuss a couple different types of this. This one here, you can see you have your handle, you have your tube coming in here, and then at the nozzle right here, you can see you have a wire guide and contact tube that's coming down through the wire, and then within that, coming out of that, we have our consumable electrode, and we see this gaseous shield coming out from around here, which this down, you can see there's that arc that we're talking about, a arc between the electrode and the components. So there's our electrode right there off of this right here, the consumable electrode, and our components down here, which is the base material. That creates the arc right there, melting it, and we can see the metal weld forming. So that was an example of one type of arc welding. There are other types of arc welding we can look at here. We have a shielded metal arc welding, or what's also known as stick welding. We have gas metal arc welding for metal inert gas welding, or MIG welding. You have gas tungsten arc welding, or TIG welding for short. Then you have your flux core arc welding, submerged arc welding, and plasma arc welding. Let's take a little bit closer look at that first type of welding, our shielded metal arc welding or our stick welding. We're dealing with stick welding. We have our diagram over here that shows how this is done. We have our power source, our grounding wire, and our electrode lead. We can zoom in up here and see where the grounding wire clamps into our base right there. There's our electrode, our flux jacket, our metal filler. We can see that gaseous cloud and our metal particles. So the thing to note about stick welding, this is consumable electrode that is fed into the arc. We have that flux coating that we can see up here on the exterior of the electrode that forms an inert gas, and this is typically used only for our steels. So now I want to take a look at MIG welding, or our metal inert gas welding. So within this is something that you might even have in your garage. It's a little bit easier to use. With MIG welding, we have a wire electrode that's going to be fed from a reel through the tip of the welding torch. So we have down here is the tip of our welding torch right here. And not only is this electrode going to be fed from our reel out through this, but we're also going to be simultaneously feeding our gas down through this. So you can see there's our wire electrode and there's our gas shield. So there's the wired electrode right there. You can see our gas shield around it. So what happens with this here is the gas is going to forms a plasma to sustain the arc and channels the weld material from the electrode onto the weld pool. What this uses here is it uses the CO2 as a shielding gas, and this can be used for aluminum or carbon steels. When you're doing it with aluminum, you do have to be really careful, and again, you're changing your temperature settings, your feed rate, and all the parameters of that there in order to use it for different types of metals and different thicknesses of metals. So the next type of welding I want to take a look at is our TIG welding, or our tungsten inert gas welding. So within this type of welding, what we have is a tungsten electrode that's not a consumable. So there's our electrode right there. We're using inert gas from our nozzle right there. So you can still see our inert gas coming out of our nozzle. Now the benefit to TIG welding is this can be used on thinner metals and non-ferrous or dissimilar metals. So that's the benefit. Whereas MIG, you might be able to tweak the settings enough to be okay and get some decent welds. But if you've got some really thin stuff you're dealing with or non-ferrous metals, then this TIG welding might be a better application. It can be automated, and that's great in a manufacturing setting. But if you're doing this by hand, personally, I've found that this takes a large skill set and a lot of practice, and I am absolutely terrible at TIG welding. I can fake my way around with a MIG welder, but TIG welding definitely takes a lot of practice and a skilled user to do this, and I actually had to employ the skilled trade of my brother, who was very good at TIG welding, to help me with my motorcycle frame when I needed some parts welded. So next I want to take a look at flux core arc welding, or FCAW. Within this type of welding, we have a tubular wire that has a core filled with a mixture of fluxing elements, deoxidizing, denaturing agents, and alloying materials. There's also elements that are going to help to increase toughness and strength, improve corrosion resistance, and stabilize the arc. Now you can provide an additional shielding agent. This can be used from an externally supplied gas or a gas mixture as well. Typically what this is used for is when you need to weld your stainless steels. Next, we'll take a look at the details of our submerged arc welding. Within our submerged arc welding, we have a consumable electrode that moves along the weld line, and there's a line of granular flux is going to be piled up on that line. So we can see that granular flux right there piled up as we're moving along that line. The flux melts into the molten slag, filling the weld line, and this is used for thick sections. So if we're looking at our plasma arc welding, what occurs here is we have an arc that's going to be generated from a non-consumed tungsten electrode. So there's our non-consumed tungsten electrode right there. And we have a plasma gas separate from the shielding gas is going to be pumped through the tip through a fine bore on the inner nozzle. So you can see that right there in the green right there. So that's separate from what we have on the outside right there, our shielding gas in our gray right on the outside there. The arc is going to be constricted by the plasma flow, and therefore a high energy concentration is achieved with relatively low currents. So for resistance welding, we're using resistance to actually heat up the metals. So in this case here, we have an electric current is going to be passed through the materials that we need to be joined together, and this is going to heat it up until it melts. So one thing to note about this here, there is going to be a need for compression when we're using this here. So you can see we have on either side of this, we have a force being applied right there. So we need some compression. There is no filler, but we may need vacuum or an inert gas as well for our resistance welding. Another type of welding that can be used is solid state welding. This is when a bond is formed by either diffusion or deformation. There's no filler, and this can bond different types of materials. You could do a metal ceramic, something like that. So that's a huge benefit right there. We have dissimilar materials that we could use. This also includes friction welding. So here's an example over here. You have a pressure force coming in. On this side, you have a rotational force going here. This is a non-rotating workpiece right there. You can rotate that, and what you end up with for your weld is something that ends up looking like this, but you do have this upset region right here where the two materials are joined. Now some other types of metal joining that we can discuss here. This is where the material does not melt. You have your brazing. So you have filler alloy used to bond things together. You have soldering. This is a lower temperature alloy there, and again, you can use this to fill. So a lot of times these are used more for electrical conductivity, things like on circuit boards, rather than structural stuff, because we're not actually melting material there. Another example here, we have heat from an iron, a furnace, induction, torch. So as we're using these things, as we're soldering, as we're brazing, we can use these types of heat sources right there. So you've already heard of soldering iron. Some of the soldering that I do for some of the antennas I make, I actually end up using a butane torch to get the surfaces of the metals heated up a little bit more and then touch the solder down to it. So there's different techniques within soldering and brazing that we can utilize when we're discussing metal joining. So one of the things we want to consider when we're deciding which type of welding we're going to use is the weldability of the materials that we want to join together. So we can see we have the different types of metals listed in these two columns here: carbon steel, malleable iron, stainless steel, aluminum alloys, lead, copper, all these different types of metals there. And for each of these, we can look at either arc or gas welding. And for these here, we have this little code that tells us that G is good, commonly used, X is not used, and F is fair, occasionally used under favorable conditions. So for each of these, we can take a look at these different combinations and decide what would be the best type of welding we should use for the materials that we're trying to weld. So now that we've looked at all these different types of weldings, what we need to ask ourselves next is, what is the strength of our welds? And with this, there are some material concerns. What are the matching material properties of the weld filler material along with the base material? So we can reference back to some of those tables and charts. There's also some standards that are going to be provided by the American Welding Society, or AWS, and also ASTM, our American Society for Testing Materials, when we're looking for that information. So how can we increase the strength? Well, how we can do this is we can increase the cross-sectional area. So you think about this right here. You have a straight cut right there. That's not going to be quite as long, looking at this in 2D right there, as if we cut this out here and do this V right there that we talked about before at 60 degrees. All of a sudden now this is longer here, giving us a bigger cross-sectional area. Then we have these other double V down here, and then we have a bevel over here. So we have all these different options here in order to increase that cross-sectional area, which will then increase our strength. So let's take a look now at some governing equations when we want to calculate the strength of our welds. So we said here before that if we increase the cross-sectional area, it'll increase our strength. So let's look at these actual calculations. So what we have down here on the left side is we have a concave weld bead, which is very poor practice right there. And you can see what this does when it's concave here, this value for T from there to there is going to be a lot smaller. So if we have a good convex weld bead as we have over here, then our T goes from right there to right there, and we can see that this distance right here is going to be bigger than our concave weld bead right there, giving us a stronger weld. And our T value, how we measure this here, we could do out some trig or geometry here, but we see that T is equal to the square root of 2 over 2 times our H value. Well, there's our H value right there and right there equal to each other. So what we have from that is T is equal to 0.707H. So coming into practice right here, here's an actual good weld. So you can see there's the weld there. So if this is our H value here, and this is our H value here, then coming down this right here would be that T value that we can calculate by that 0.707 times our H value. So now let's take a look at a butt weld. For this right here, we want to calculate the strength of our butt weld right here. So if we're dealing with this situation where we're in tension, we have our load P here and our load P over here, pulling this in tension. If we want to find our strength right here, our sub y, this needs to be greater than our stress, and our stress was defined by our load over area, where we can come up with our area right here as our height, h, times our length, L, and this is our length L right there. So h times L will give us our h, so P over A, or P over HL, will give us our stress right here, our sigma, so our S sub y is going to be greater than our sigma. So that was the case when we were in tension. What if we're in shear? So we have the situation now where there are our loads being off the sides here and putting in tension. We have our loads going this way and this way here, putting this in shear. So we still have that same H and our same L right there. So this right here, we have our general relationship for shear stress. Remember, is load over our area. Our area is the same as before, our H times our L value. And this now, for our shear, this is saying S sub y over 2 is going to be greater than our shear stress right there, or our P over our HL. So now let's take a look at some calculations and equations for the strength of our fillet. So for this here, we have the area, if we're talking about in parallel, the area over the diagonal or throat length from the tip to the midpoint of our hypotenuse right there. So if this is our hypotenuse here, and this down here is our tip, if we zoom in on that, what we have here is that distance from here to that midpoint right there. That is our T value. So our T value comes from this equation here. T is equal to the square root of 2 over 2 times our H, where this is our H from there to there, and this right triangle on both sides of that. We can do our math, and we find that to be is T is equal to 0.707H. So that distance right there where that arrow is. Now from that, we can find our shear right here. So our shear stress is equal to our P over A. We can put in our area now there. So P over our area for this case here would be that value right here of our 0.707H, that distance right there, times our length. Well, what is our length? Well, our length is going along here of our weld. So this is our length right there. So if we multiply that value for T times that length right there, that's going to give us our area that we're going to use down here to calculate our shear. So as we continue on with our discussion for strength of a fillet weld, what we have here shown below is what we saw at the beginning of this module here, a lap weld. For this lap weld here, you can see we have this load P and this load P right here, and here's our weld. For our weld, this is our H value, and our H value here. This is our hypotenuse, and with our hypotenuse, we have this distance from there to there, which is our T that we've calculated and shown a relationship for. And if we went into the board in our third dimension, this length going this way would be our L value there. So our governing equations related to that, we saw on the previous slide that our shear stress was equal to our 1.414 times that P value right there divided by our H over L. And for our yield strength over 2, this is going to be greater than that relationship there for our tau, or this 1.414 times our P over HL. Now we can also relate this back to our normal stress here, our sigma value right here, and we can see that our yield strength is need to be greater than our sigma value, which is equal to that P, that same P right here, our load right there, over our H, which again, our H value is this distance right here, and our L distance, which goes into our board in that third dimension. So now if we want to take a look here at our strength in bending and torsion, for bending we can determine the normal stress at flexure formula at a distance to the weld. So we can come over here and we can say that our yield strength is going to be greater than our sigma sub x, which is equal to our mz, there's our moment right there, times our y, this is our y distance right here, all over our I value, our moment of inertia. So we can come over here, we take a look at this, there's our tau max. Let's see if we can erase this here. There's our tau max. Out here, there's our h over 2, and this is our shear stress value all the way up until we get to our, at the top right here, our peak right there at the max shear stress value there. We can calculate the shear load and use our previous relationships for our shear stress. From that, we can see now that we have our yield strength R sub y over 2 greater than that tau sub yx right there, which in this case here is our v sub y times our q over it, which again, this is our previous relationship for shear stress that we have earlier within this course. Now, if we're dealing with torsion, we can determine the torsional stress at a distance to the weld as well. So we have this relationship here. Sy over 2 is greater than our tau. So for this situation, for our torsion, we have the relationship that we've seen previously of our torque times our R over our polar moment of inertia, our J value there. Next, we're going to go through my hand solution to an example problem that utilizes the theory and governing equations we talked about within this module. So take a look at this example here, where we have a butt weld going on here. So this we recall from earlier. So there we have a butt weld there. Two 15 millimeter steel plates using an E70 series welding rod. So we know we have a steel plate and we know the material we're using for our welding rods. They give us our SY in this is 400 MPa. They give it to us our diagram as well. They tell us our weld length here is 90 millimeters, and they also tell us that we have a safety factor of 3, and with that safety factor of 3, they want us to calculate what is the maximum tensile load. Let's take a look at problem 11.2. In this problem here, we have two 15 millimeter steel plates with a yield strength given to us as 400 MPa. These are butt welded using an E70 series welding rod. So this is going to be important when we look up our properties here. And good welding practice, which is going to go into our assumptions. So the wording here is important as far as our assumptions we make. The weld has a length of 90 millimeters. And that they're asking us to find is the maximum tensile load that can be applied to the joint safely with a safety factor of 3. So they give us our SF of 3 there. They also give us this diagram here, 11.2. So we can see here are the two steel plates, 15 millimeters thick, two forces going out this way, and here's our butt weld right there. So we know the weld length, 90 millimeters. We have our yield strength of 400 MPa, our safety factor of 3, and we know it's an E70 series weld. So we've had a chance to read through the problem statement and look at the given schematic. The next step we want to do is write out our solution to the problem. On the first page being the same as before, we want to write down everything that they give us, simplify down the given diagram, figure out what they're asking us to solve for, and to make any assumptions that we can from the problem statement before we start a solution. So the first thing that we do is we take a look at that problem statement and everything they give us and write down what we know. So we're given the fact that there's two plates. We know the thickness of these plates is 15 millimeters, so we can write that down here, that our thickness is equal to 15 millimeters. And we know that it also tells us in the problem statement that our yield strength is 400 MPa. Now it tells us we're using E70 series welding rod. So that's going to be important when we go through and figure out a couple of properties for that from our book. We'll reference back to section 11.4 for that. It tells us that our weld width is 90 millimeters, and we have a safety factor equal to 3. Now the thing to think about here is these are in millimeters. We may need to convert these to meters when we go through and solve for a final solution. So they want us to find the max tensile load that can be applied to the joint safely with a safety factor of 3. So we know, again, we have a safety factor of 3 here. And from the problem statement as well, we can go through and figure out that we have a weld efficiency of 100%. And that's given, if we go back to our problem statement, it tells us that it's good welding practice. So with that good welding practice, we're assuming a weld efficiency of 100%. So now we want to go through and begin our solution. And where we want to start for our solution is with section 11.4, where we're taking a look at the specified yield strengths for E70. So now we want to take a look at section 11.4 from our textbook. And this is on page 334. This is for welded joints subjected to static, axial, and direct shear loading. There's a lot of good information in these first three paragraphs here that you should read through, but where we want to concentrate, let's take a look down at the fourth paragraph here. So in the fourth paragraph, it says that welding electrode material strength and ductility specifications have been standardized by the American Welding Society, AWS, and the American Society for Testing Materials, ASTM. So we've heard of both of those societies before. Now for us specifically, for example, welding electrodes that we're looking at in our problem here in the E60 and E70 series, where we're looking at the E70 series, are designated E60XX and E70XX. Now, the 60 and the 70 indicates tensile strengths of at least 60 or 70 KSI, respectively. So we're looking at tensile strength here of 70 KSI. Now, the last two digits indicate the welding process details, not necessary for our specific problem right now. Specified yield strength for E60 and E70 series. So now we're looking at yield strength. So this is what we need to actually come up with, are about 12 KSI below the tensile strengths. So we want to subtract 12 KSI from our 70 KSI of the tensile strength for our E70 series. So for the next step in our solution, we go back to our assumption where we assumed 100% efficiency based off of a problem statement. And now we want to find our max tensile load that can be applied with a safety factor of 3. So recall this relationship here for our safety factor. The safety factor is equal to our yield strength here times our area over the force, where we're looking for force. So what we want to do is rearrange and solve for F. So F is equal to our SYS times A all over our safety factor here, where our A can be found by the dimensions given in the problem statement. We have the thickness and the length. So we convert from millimeters to meters. So this is 0.015 meters times 0.09 meters. Instead of 15 millimeters and 90 millimeters, we now convert to meters here. So we have an area based off of those dimensions there. We have a safety factor of 3. And we found our value for our yield strength here, 399.6 MPa. We can plug that in. We end up with force is equal to 399.6 times 10 to the 6, because we want to convert to pascals and not megapascals. So our units work out are 0.015 meters, 0.09 meters divided by 3, which when we plug this in, we end up with a force, which is our max tensile load that can be applied of 179.8 kilonewtons. Now let's take a look at problem 11.3. So in this problem here, we have two different steel plates where the yield strengths given to us is 50 KSI. These are attached by 3/8 inch parallel load fillet welds. So it tells us the weld thickness and tells us parallel load fillet welds. These are shown down below in this figure here. It's an E60 series welding rod, so we can go back and use that information there to look up the properties about the welding rods. And good practice, good welding practice. So again, that's going to give us some information as well for our assumptions. Each of the welds, it gives us a length of 3 inches long, and it tells us a safety factor is 3. Now they want us to find the maximum tensile load that can be applied based upon that safety factor. So now we can take a look down here. Here's our given schematic. You can see the loads right over here. Here's your weld length of 3 inches. It's an E60 series welding rod that's used. Yield strength is given to us as 50 KSI for the plates. H is equal to 0.375 or a 3/8 inch. Safety factor is equal to 3.
And we'll note here there are 2 of these 3-inch welds, so that's going to be important as well as we're solving this problem. Now that we've had a chance to look through the problem statement, the next thing we're going to do is organize this in the correct format. So we want to figure out, what do they give us, what are they asking us to solve for, what assumptions do we make, and from there we want to figure out a plan for how we're going to move forward and what key equations we should use. So for example, 11.3 here, what do they give us in the problem statement? Well, they tell us that we're using E60 series welding rods. They give us an H value of 0.375 inches, which is the height of welds. They give us a yield strength of 50 KSI, and they give us a safety factor of 3. And then we redraw out our schematic over here. Okay, we can see we have our weld length over here, 3 inches as well, given in the schematic diagram. We have our forces out here. We have our 2 different plates. And what do they want us to solve for? Well, they're asking us to solve for the max tensile load that can be applied here to stay within our given safety factor. So from this and the wording of our problem, we can make 2 assumptions. One, throat length is given by T equals 0.707 H. Now, the next page here, we're going to go through and how we come up with this assumption, where this comes from. Where this is going to look at is back at figure 11.7 on page 335. So assumption 1, we're going to go through a whole derivation on where this comes from and how we can get this from this figure. The second assumption we're going to make is that the weld efficiency is 100%. So from our assumption, we determined that we needed to go take a look at figure 11.7. So shown here is 11.7. What we want to look at is part A up here on the right hand side. So this is the type of weld that we have going on for our specific problem. So if we zoom in at a 2D cross section of the 2 plates in the weld here, we can see up in the top right, we have this geometry going on, where you have the height going up this plate as H, the length going over here is H as well, and then you have our hypotenuse here that'll have some known value, and then thickness, you can see, is this diagonal length here, the max thickness of this weld. And this is given to us in the chart as T is equal to 0.707 H. So reference to H being the height and length of this weld here. So what we're going to do now is break this down and go through a little bit of the math behind how we come up with this value for T relative to H. So taking the information from figure 11.7a in our textbook, what we want to do now is break down the geometry behind what they give us in the diagram and figure out how they come up with our relationship between T and H. So this is a simplified version of the diagram for figure 11.7a. We have a right triangle here. We know height of H, length of H here. Then you have this hypotenuse over here of C. And then T is this max distance here, right up the center from our bottom point down here to the center of C over here. So we want to figure out, how does T relate to H? So there's a couple different ways to do this. The way that I'm going to go through here is going to go through Pythagorean's theorem. So we say a squared plus b squared is equal to c squared. So in our case here, there's your a, b, and c, or h, and c. So we do this out here, h squared plus h squared equals c squared. Rearrange it. H squared plus h squared becomes 2h squared is equal to c. Then I'm going to divide both sides by my 2. So if I divide both sides by 2 here, I end up with h squared is equal to c squared over 2. So now we're going to do the same thing for just a portion of this. So if we want to do with t here, what I'm going to do is take a look at, let's just take a look at this right triangle over here. So if I take a look just at this right triangle over here, c becomes c over 2 for this length between there and there. Then I have my t and my h, so we have a right triangle. My hypotenuse now is h, and my sides is t and c over 2. So I redraw that out over here. Here's my right triangle. Here's c over 2. Here's t. Here's h. So if I use Pythagorean's theorem here, I can say that t squared plus c over 2 squared is equal to h squared. So that's what I have, t squared plus this over here is c over 2 squared is equal to h squared. Now I want to go through and solve this for t. So I rearrange it a little bit, move this back over the other side. So t squared is equal to h squared minus my c over 2 squared. So I take a look at this here and say, okay, I'm going to square this out to take into account the fact that this is in parentheses here. So now I have that t squared is equal to h squared minus c squared over 4. So I'm going to pull out a 1/2 here so that I have a c squared over 2. So I pull that out front and I have t squared is equal to h squared minus 1/2 times c squared over 2. And the reason I want to do that is because my c squared over 2, I have a relationship from my Pythagorean theorem from the entire triangle up here. So c squared over 2 is equal to h squared. So I can replace this with an h squared, which does exactly what I want to do and eliminates c to get it in terms of h. Because if we recall, we want the formula in terms of t and h, not in c. So all of this is to eliminate c from this here. So I plug in my h squared for my c squared over 2 here. I end up with t squared is equal to h squared minus 1/2 h squared. So h squared minus half h squared, we leave here. Now I'm going to take the square root of both sides. So t squared is equal to the square root of h squared minus 1/2 h squared. So h squared minus 1/2 h squared is simply 1/2 h squared. So t is equal to the square root of 1/2 h squared. Separated out, t is equal to the square root of 1/2 times h with the square root, this is 1/2 there. Square root of 1/2 is equal to, t is equal to 0.707. Move the paper up so you can see that there. So again, we said t is equal to the square root of 1/2 h squared. So this then breaks down to t is equal to the square root of 1/2 times h. So we can break that down again. The square root of 1/2 is 0.707. So t is equal to 0.707 h, which is exactly what we were given in our assumption and where we pulled this from figure 11.7a. So now that we have an expression here for t, which we just derived from figure 11.7a, the next thing we want to do is use that information to calculate our throat area. The throat area is going to be this value for t times the length of the welds. Now the thing to think about here is we have 2 welds, one on each side of that, so it would be 2 times L. So we multiply this length for both the welds times our t value here in order to get our throat area. So we're in this problem here, we have a value for h given in our problem statement, and we have a value for L given in our problem statement as well. So we can plug in these numeric values here. We know that given to us, h is 0.375 inches, and the length, again, is 3 inches, but there's 2 welds, so don't forget that 2 when we go through and calculate the throat area. So we plug this back into our throat area equation here. We have our t value times our length. So we plug this in, 0.707 times 0.375 inches for h value, times our length here, times 2 for both of the welds of 3 inches. Calculate this out, and we end up with a throat area is equal to 1.59 inches squared. So now that we have this here, the next step is to go through and calculate our yield strength. And we're going to go back to section 11.4 in our textbook in order to come up with this relationship here. So now we head back to section 11.4 in our textbook. This is welded joints subjected to static, axial, and direct shear loading. What we want to do is concentrate down here on the 4th paragraph. So in the 4th paragraph, what we have here is that a welding electrode material strength and ductility specifications have been standardized by the American Welding Society, AWS, and the American Society for Testing Materials, ASTM. So for us, we have a little example here that welding electrodes in the E60 and E70 series, where we're interested in E60 for our particular problem here, are designated as E60XX and E70XX, where the 60 and the 70 are going to indicate the tensile strength of at least 60 or 70 KSI. So what that's telling us for our problem is for E60 that the tensile strength is going to be a minimum of 60 KSI for our problem there. So that gives us that information. The last 2 digits indicate the welding process details, which we don't have to worry about. The next part that we are concerned here is for the yield strength. So specified yield strengths for E60 and E70 rods are about 12 KSI below the tensile strength. So for ours here, it's going to be 60, which is the tensile strength for E60, minus 12. So that's where we're going to get our yield strength from, is from this relationship here of 60 minus 12 KSI. So that brings us back to this relationship here. So now we've just seen from section 11.4 in the textbook here, we can get our yield strength to equal that tensile strength minus our 12 KSI for the E60 rod. So this gives us an SY of 48 KSI. So the next step after that is to take a look at our distortion energy theory. So this comes from figure 6.10 on pages 177 to 179 of our textbook. So now we can go back in our book to chapter 6 and take a look at figure 610. And again, this goes between pages 177 and 179 for this section in our textbook for distortion energy theory. So this is our plot for distortion energy theory. And what we want to pay attention to is the distortion energy theory predicts that the shear yield strength is the square root of 3 over 3, or 0.577 times the tensile yield strength. So this is the information we're going to use and the equation we're going to use in order to write down our shear yield strength for our problem. So taking that information from figure 6.10 back on pages 177 to 179 of our textbook for distortion energy theory, we now can calculate that our shear yield strength is given by this relationship of the square root of 3 over 3 times the tensile yield strength. So this ratio of square root of 3 over 3 becomes approximately 0.58. So SSY is equal to 0.58 times our SY to get our shear yield strength from our tensile yield strength. So plug this back in for our particular problem here, where we already calculated our S sub y earlier in this problem is 48 KSI. So we can plug this in here, and now our shear yield strength is equal to 0.58 times SY is 48 KSI. So our shear yield strength is equal to 27.8 KSI. From there, now we can go through and calculate our tensile load. So we have this relationship here that our force here is equal to our SYS, or our shear yield strength, times our area divided by our safety factor. Now for our problem here, we've just calculated that our shear yield strength is 27.8 KSI. Our area, we've calculated earlier, is 1.59 inches squared, which is our throat area here that we can plug in. So plug in our known values. F is equal to, when we take KSI and put it in terms of PSI, 27,800 times our 1.59 divided by 3. Pay attention to our unit analysis for this, and we do end up with pounds in the end of 14,700 pounds for our tensile load.